Very good. Good morning, everybody. I'd like to welcome you for the second of this tutorial. I see you all ready to get your hands dirty with the Sensei infrastructure. So I'm going to give the word directly to Berlin to really apply today a lot of the things we've seen yesterday as background material, and today we're going to really concentrate on the Sensei interface. Okay, so Berlin, please. Thank you.
Absolutely. Yep. Today we're gonna focus on first thing we're gonna do is go through a bunch of examples with Sensei, and we're gonna do like a deep dive into these. We're gonna talk about how you would instrument a simulation or mini app, how you would write a data adapter and go into the code of that, and also how you would write an analysis adapter and go into the code of that. So the data adapters are really for the simulators, for the folks writing the simulation. They need to present their data to the consumers. And so that's what the data adapter's for. So we'll focus on what's involved in writing a data adapter and go into that deeply. And then the analysis adapters are the consumers of data, or the backends that do the rendering, analysis, processing, and we'll look at examples of how to do those. And then we'll also look at the bridge code. So the bridge code is what manages the data adapters and what the simulator has to do to instrument their code with Sensei to actually use it. And we'll go through a number of mini apps. We'll look at oscillator autocorrelation example. So oscillators is this mini app that just has some oscillators where you give it a configuration file specifying the position and the 3D volume of these oscillators, and the oscillators are like a sinusoid and they're damped. So you can set the frequency and the strength of the damping. And the analysis for that is an autocorrelation. So the autocorrelation is a signal processing technique, and we can find the locations without knowing anything about where the oscillators are positioned. Using the autocorrelation, we can find the locations of the sources in the volume. So it's kind of a toy demonstration, but it's an interesting one in that it's a time domain analysis. So that it's also one that we use to benchmark the code. We'll look at lamps and Osprey. We'll look at a Catalyst live demo, and we'll look at a Python and body code. So with that, from the simulations point of view, the simulation writer, what would you have to do to use Sensei? We call that instrumentation, adding that code into your simulation. So the first thing you want to think about is your data and the data adapter. We have in Sensei a thing called VTK data adapter. This is a data adapter that implements all of our API, all of the methods. And to use it, all you have to do is create a VTK object and pass it in. So if in your code, if you're using C++ or Python, you can create a VTK object very easily and then just pass it in here, and you won't have to do any other coding. So that means you can limit your coding to constructing VTK objects. That's not always possible. It's not always desirable. So for Sensei 1, this is a pretty good option because we only have one mesh. In Sensei 2, when we have the possibility of multiple meshes, and when you start thinking about in transit and you have multiple meshes, the VTK data adapter's less desirable because that means all of the meshes would get sent over the wire, and that would be kind of inefficient. So take that with a grain of salt, but this may be really an easy way to get something going. And if you just have to transfer one mesh and you know exactly what you're sending, this is also a good option. If you don't use that, then you will implement your own data adapter using polymorphism in C++. Second thing you want to think about is your analysis. What are you going to do with that data? If you can use the existing analyses like Libsim or Catalyst, you're good. You can just use the ones that come with Sensei the analysis adapters. But you also have the option to derive a new Sensei analysis adapter. And this is good for special purpose cases. If you have a new renderer, new rendering method, if you have some kind of numerical analysis that VTK or ParaView Libsim does not do well. Some of the examples I could think of are like topological analysis, computational geometry, machine learning. There are a lot of things that Libsim and Catalyst don't do very well. Finally, the bridge. The bridge is the code that manages these adapters. So we usually think about the bridge in terms of initialize, compute, and finalize. Initialize sets everything up. Compute is what you periodically call from your simulation to push data into Sensei or through Sensei into the analysis. And finalize cleans everything up. So the bridge is very simple, but it's actually the code that ties everything together. And the instrumentation is actually putting those calls into your simulation. So this is the roadmap for how to use Sensei right here. Okay, now we'll start getting into the example of the oscillators mini app. This is a parallel C++ code. It's damped oscillators, as I was saying. Takes a file that specifies the position of these oscillators. You can tell where they're positioned in this animation. But you could actually position them anywhere. You can set the frequencies, the magnitude, and the strength of the damping to make it more interesting and challenging. So yeah, that's a good summary of the mini app. And it's a parallel mini app, and it uses the piecewise parallelization strategy with a multi-block. So you can tell the mini app, you can run it with MPI, and you can tell it how many blocks to make, and it does all of the domain decompositions and whatnot. So starting off in the instrumentation process of the mini app, most of the work is in creating the VTK data sets. And that, of course, happens in the data adapter. So this is the Sensei 1 data adapter API. We've got these pure virtuals. The get mesh, this is where the VTK data sets are created and returned. The parameter to this structure only. That parameter is to tell the adapter not to create any geometry. So for example, some analysis, say some statistical analysis, may just need to look at the array values itself and not care about the geometry. So if you pass structure only equals true, then no geometry is created. So for example, if you have an unstructured mesh, as Jean was demonstrating how to construct those, you've got cells with the connectivity arrays, you've got the points themselves, you've got the cell offsets and the cell types. So all of those arrays don't need to be created if that structure only is true. And that will save a lot of memory and overhead. With Cartesian meshes, it's kind of meaningless because everything's implicit. Then the add array method of the data adapter. So this method takes the mesh object. That will be the VTK data object that's returned by getMesh. The association, so the association is a numeration from VTK saying if it's point data or cell data, so telling the centering of the array, and the array name. So add array is what an analysis adapter will call to say, I need pressure, I need temperature, and I want pressure on the cell nodes. So this is how the analysis adapter gets specific arrays that it needs to process and compute its result. Now, these two functions, get number of arrays and get array names, are about metadata. So the analysis adapter can know what the simulation can provide. And so get number of arrays, association here is the type of centering, cell or point. And this is a VTK enumeration. So you can call, the analysis adapter can call it and say, get number of arrays for point data, and it will return, say, 5. Then it will know there are 5 point arrays, and then for each of those 0 through 4, it can pass in the index and the association again, and get the names of those. And finally, in the data adapter, we have release data, which is called after every iteration, and it's just basically to say, okay, you can clean up whatever values you've cached and free up memory if you can. So diving in deeper into this. So this is for the oscillators mini app. This is the data adapter for that, and we can find this in the VM. It's in the Sensei repo itself. There's a folder in the Sensei repo with mini apps and oscillators. So in this code, we're ignoring the structure-only parameter. Why are we doing that? It's because we're making image data, and it's kind of irrelevant in that case. So what's going on here, if we don't have a mesh object already created, we're going to create a new multi-block data set in VTK. And this smart pointer is kind of something like standard shared pointer. It implements all of the ideas that standard shared pointer implements, however, with the VTK memory management scheme. So when you're using these, you can be relaxed about your memory management because you know when this pointer goes out of scope, it's going to release its reference. And also when you assign to another smart pointer, the reference count will be incremented automatically inside that other smart pointer. So we're going to set the number of blocks, and this is just some information that the application carries internally to know how many blocks there are. And for every block that we have internally in the mini app, we're going to go through and we're going to call our get block function and pass it into the VTK multi-block data set at the right index. And then in this example, we're just going to add the array here into the data set. And in general, I don't think this is a good idea, but it's what they did here. And at the end, return the whole thing. And now, so this function right here, where we're calling get block mesh, this is what happens. And in here, we're actually just creating the VTK data set. So in here, we're setting the extents, the spatial extents that tell where the block is positioned. And so we're not setting the origin, the spacing. So those have default values of 0, 0, 0, 0 for the origin, and the spacing is 1. So we're just going with the defaults. And this tells where the block's positioned using those defaults. So there you have the get mesh function. So get mesh, again, is for creating the VTK data object that is used to store the simulation's geometry. So the add array method next. Again, here in addArray, we're expected to be passed in the mesh that we're going to add the array into. We're told whether it's a point or cell data that the analysis is after and the name of that. So let's look. We're ignoring the association here because in this mini app, there's only cell data. And so we're being a little bit sloppy. We're not doing any error checking. We're not telling the caller, hey, you asked me for point data. You made an error. We're just ignoring that. Now here, this is something you're going to have to do because you're passed in the mesh object as a VTK data object. This is, if you remember from yesterday, the class hierarchy we showed, this is one of the base, very low-level classes. We're going to have to downcast that into a specific, data set type. And this VTK multi-block safe downcast, this is kind of a wrapper around casting for historical reasons in VTK. In the 90s, not all compilers did dynamic cast correctly. So this is really ancient kind of craft in VTK. You can replace this with a dynamic cast to a VTK multi-block dataset star. So this is a dynamic cast to get the VTK data object into the multi-block dataset type. How do we know it's a multi-block dataset type? Because we actually just created the mesh in our get mesh function, and we know. So if you really wanted to write bulletproof code, you'd actually test this to see if after the cast it was null, and you would know somebody passed you the wrong object, and you could throw an error. In this code, there's not much error checking going on. So if somebody were to call this incorrectly, it would just crash. But that's probably not going to happen. So then we're going to look inside the multi-block data set to get the number of blocks. And we're going to loop over those. If they're not null pointers, so recall that the multi-block data sets are these trees. The data sets that are local on the multi-block, the nodes that are local, have non-null pointers with the data objects in them. And all of the nodes that are remote and off rank are null pointers. So we're checking here if the node in the tree is if it is a null pointer, then we're just going to continue and skip it. Otherwise, we're going to get a reference to that node. And we're going to get the cell data out of, so this is our internal cache of image data nodes. We're going to get the cell data out of those. We're going to get the array. So this is a call into VTK cell data. Cell data is a container of VTK arrays, and it's a dictionary from strings to arrays. So we're gonna try and get the array. And so what this chest does is says, okay, if the array is already in the data set, then we skip it. We don't have anything to do. If this returns null, then that means the array that we're looking for has not been added to the dictionary yet. And so we're going to create a new instance of a VTK float array. We're going to set the name. That's very important. If you don't set a name, VTK will crash. And then we're going to use the zero copy data transfer to get the pointer that we have cached internally, pass it the number of cells, and this one is the save flag. So we're telling VTK not to delete it, that we own that array. And then we're passing it into the cell data container. And this call is sometimes necessary. set active scalars, it tells VTK, when you're using VTK pipelines, there's this concept of active scalars and active vectors. These are, when you set something to be active, that's what gets processed when you connect filters that require a specific array. For example, if you connected a reader to a vector magnitude computation, then that vector magnitude computation would call get active scalars. And that array would be used to compute the magnitude. This is just deleting this array because we called new here. So we created a reference. And then when we did this call to set scalars, we passed it into the container, and the container creates a reference. So to avoid a memory leak, you have to delete it. And fast delete, I don't use that very much. You can just call delete. Fast delete, I think it skips some steps, but is essentially just the same as delete. And now we're telling the return value, setting it to true, which will tell the caller that yes, we added it. However, this test is usually or will always fail, and it will be skipped because up here in our get mesh function, we had done this. We had called the add array here. Actually, with this call, this call will initially cause the array to be added. It will go in here. If the analysis adapter calls this again, though, then this will be bypassed. The array is already in the mesh. OK, so that's the data adapter. I mean, so we did here. We're skipping these calls, but they're actually one lines. So get number of arrays, it will just return a 1. Get array name, it will, at the very least, it will just return the name data. That's what we're using. That's specified here. So those are very simple functions, one-line implementations. They can just go in the header. Unless you want to do some fancy error checking where you check and see if the caller is passing in the right association and so on. But in the mini app, it's just a toy example. There's not much error checking, so they're just one-line examples. And then the release data will release any cache data that we have. So that's the data adapter. So now on to the bridge. The bridge code, again, manages the analysis and the data adapter. And it provides the hooks for the simulation to push data through Sensei to the analysis. And typically, the bridge is comprised of three calls. Initialize, compute, and finalize. In the initialize call, in this mini app, we're just going to store pointers to the meshes, our internal representation of the meshes. The oscillator mini app doesn't use VTK internally, so we're just going to take pointers to the internal data structures and cache them. Then in our get mesh call, we'll be able to look those up. Second step in the initialize, specify what analysis will be done. And so we're going to use the configurable analysis class. That lets the analysis be selected at runtime through this XML file. We talked a little bit about that yesterday. The compute method. Inside of our mini app, we've got set dataset and analyze. And in our benchmarks, we can disable these. And so we use this mini app for benchmarking, so you could turn off Sensei completely. And so we could compare how the code runs with Sensei and without Sensei. And then finalize, we're going to free up the data adapter and the analysis adapter. So our initialize function, let's dive down into that for a sec. So we need to pass in the communicator, the number of blocks that we're going to run with, the number of local blocks, the length, of the whole box size, and a config file, and these integer pointers. So from XYZ to XYZ. So these are little arrays that specify the extents, I think. So we're going to create our data adapter. This is our data adapter class, which we just went through. We'll create an instance of that. We'll store it. This global data adapter is a global variable, so we've used global to denote that. We're going to tell it how many blocks, set the initial time step. For all of the local blocks, we're going to go through and we're going to cache these block extents that they're going to be used when we create the VTK object. And we're setting the whole extent in VTK terminology, the size of the global data set. So here we're caching the size of the local blocks. Here we're setting the size of the global. Finally, we're creating our configurable analysis adapter, and we're initializing that with a communicator and that XML file. So there's the initialize function in the bridge for the mini app. When we execute the in situ, the mini app's going to call compute every time that it updates its internal state. When that happens, it's going to pass in the time. We're going to pass that into our global data adapter through set data time. And this is important so that things like Catalyst and Libsim know what simulation time things are running at. We're going to set the time step, so the iteration number. Then we're going to call the analysis adapter execute, and we're passing in our global data adapter. This get pointer business is because it's one of those VTK smart pointers. They didn't implement an automatic, conversion override. So instead they chose to do this explicit function call. So you have to do this. It just gets a pointer to what's inside the smart pointer, a raw pointer. And then at the end, we're calling release data on our data adapter to free whatever memory we can. So that's really the driver function that gets called every time the simulation state changes. And yeah, we're in this. We're executing the analysis adapter. The analysis adapter is then going to make calls to the data adapter API to get whatever data it needs to compute its solution. And finally, the finalize method in the bridge. The finalize method, we're nulling these out. So these are smart pointers. Assigning a null value actually caused the internal object to be deleted. So that's actually freeing up the memory. This is important in this finalize method because things like Catalyst and Libsim, they make MPI calls. So they have to be taken down before MPI finalize. So it's important with those smart pointers because these are global variables. They only get destroyed when the program gets taken down. And that will happen after MPI finalize. So it's important that we do that here. And in Sensei 2, we actually added a finalize override to the analysis adapter API so that this won't be necessary. Okay, so the analysis itself that we're going to do with this mini app is autocorrelation. It's a statistical test of a function with itself. It tells you how much a function matches itself. It's applied through time, but it can be done over space, or both. The fancy mathematical formulation of this, and here's an example where a sinusoid function is hidden by a bunch of noise. And after autocorrelation, you can actually pick out the sine function. So it's a simple analysis used in signal processing. So let's look now. So far what we've done is we've looked at the data adapter. The data adapter is what converts data from the mini app into our data model. And we've looked at the bridge. The bridge is what manages the execution and drives and pushes data through Sensei. Now we're going to look at the analysis adapter in depth. So the analysis adapter is what actually processes the data. We have analysis adapters for Catalyst, Libsim. Autocorrelation is an example of a special, one-off, you might say, to do a different type of analysis. So this is going to be of interest. This part of the talk is going to be of interest to those in the audience who want to do custom analysis like volume rendering, like computational geometry, et cetera, et cetera. Something that Catalyst and Libsim don't do well. You're going to want to do this. Or if you care about extreme performance, this is a good option because Catalyst and Libsim both have a lot of overhead in terms of starting up and running. So to dive into this a bit, first we'll look at the initialize function. Remember the Sensei analysis adapter API is one virtual function in Sensei 1. It's execute. And the execute method takes a data adapter star. So this is, an addition to that that's used to set the autocorrelation up. We're passing in a communicator. The window, which is the parameter, like how wide do we want to do the autocorrelation? We're going to process the input signal in window-sized chunks and apply the autocorrelation to each window successively in the time series. So the window will be basically a number of time steps. The association tells whether the array to analyze is point or cell data in terms of VTK data centering, and the name of that array. And let's see, Kmax is one of the parameters. I don't recall offhand exactly what that does, but that's one of the tuning parameters for the autocorrelation. So this autocorrelation implementation, it uses this library called DIY. DIY is basically a block streaming library. So if you write your analysis function to take a block and process a block, DIY will push blocks through it. And DIY is a little bit beyond the scope of this presentation. Just wanted to point out that that's what, when you see things like DIY master, it's coming from that library. But basically, all the DIY stuff is about pushing blocks through an analysis function. And so DIY will handle the pushing of the blocks, and the computation is done on those. And so our analysis uses DIY. We're gonna, when we execute the analysis, we're gonna do some conversion from the VTK data model into the DIY data model, and then DIY will do the computation. And we're caching basically the parameters controlling the run. So yeah, this slide's absolutely wonderful. Don't worry about this. This is the execute method. We're going to look at that in some detail But right here, that shows the thing in its entirety. I can't read it. You probably can't either. We'll look at it in a bigger font in a second. So the high-level overview, the execute is passed in a data adapter object. That lets us access the data from the simulation. We're going to access those arrays. We're going to get them out from the simulation using the data adapter, and then we're going to calculate the autocorrelation. So that's what we're doing. So now, looking at this in detail, as I showed in the previous slide, the function's quite long, and it can't fit on a whole slide. So I just put this gray. It means just the code continues down below, and we can't see it. So what we're doing in this first section is when this is invoked, our execute, we're passed in the data adapter. We don't care what type of data adapter it really is. We're just going to use the API to get the data. So we're going to call the get mesh. We're going to tell it structure only is true because we don't care about the grid spacing. We don't care about the mesh geometry. We're only going to access the data arrays. So we're calling get mesh. We're return to mesh. We don't really know what concrete type it is. We don't care. At this point, we don't care. We will in a second. We are going to then call add array. We're going to pass in the mesh that we just got. This has been told to us. So we have this cache, the internals association. We're told by the initialize function whether we want point or cell data and the array name itself. And so we're telling the data adapter to add the array we're going to compute on. If we can't get that, we're returning false. And then this basically does the conversion from VTK into DIY because our autocorrelation computation doesn't use VTK. It doesn't know anything about VTK. And so I guess the point is, if you know VTK, you don't have to do that conversion. You can just grab the data out of VTK directly and do your computations. If you're trying to shove data through some other library that doesn't understand VTK, then you do that conversion, and you get the raw data arrays out. So now scrolling down further in the function, we've already gotten the data, and we've initialized our DIY block set. We have the arrays that we need in the data set. This composite data set, safe downcast. This is, again, a dynamic cast. It's wrapped in this wrapper that VTK uses. We're passing in the mesh, which is a VTK data object star, and we're expected to get out a composite data set. So there's actually two cases that we care about. We're not guaranteed that the user is going to have a composite data set. It could be just a raw data set. Because remember, in VTK, there's two ways of doing parallel. The legacy way, where every rank has one VTK data set class, or the more modern way where there's a composite data set, which is this tree. So we have to handle both of those cases. So this if handles the composite data set. This else down here handles the legacy case, where you have a data set instance on every rank. So in the composite data set case, these are tree-based data structures. Local data is not null. Remote data is null in the tree. And we can get an iterator, and we can iterate over all of the local nodes. So we create an iterator from the composite data set itself. It has this new iterator method. We're using a smart pointer again, so we don't have to worry too much about memory management. That will all be handled for us. The default is actually to skip empty nodes. So we're saying skip empty nodes off. We're going to visit all the nodes. This is an example of using the iterator. So we're going to walk over that tree. We're going to call the method get current data object. So that just returns VTK data object at the current node in the tree. And we're going to do this safe downcast again. It's equivalent to a dynamic cast to the VTK dataset. If we have one of these, the dynamic cast may fail because we may have an empty node, which means that object is remote, not on our rank. If it's local, we're going to go in. We're going to use this as part of the DIY stuff. We're going to tell it, OK, get the block ID from DIY. And this is DIY stuff again. Here, we're getting the actual array out of the mesh. So again, we're using a safe downcast. When you call this get attributes as field data, this would be equivalent to a get point data, a get cell data. But we can use this get attributes as field data. We can use this method. If we pass in the association, it will give us the container, the point or cell data container. And then we can call get array with the name. And we'll cast that into a float array star. This get array function returns the abstract class VTK data array. So we get a concrete class, the float array. And then we pass it into our, this is the DIY implementation of the autocorrelation computation. We're going to call that and pass in the array. So this FA get pointer 0, this is how you get a pointer to the VTK data. So let's just say you have some analysis routine written in C. You just need a pointer to the data. You need to know the length. This is how you do that in VTK. So that gives you a pointer. You don't have to go through VTK data array API to access tuples or whatever. You can just do this and get a float star. And this parameter tells VTK how far to offset the pointer. So you could get a pointer to 10 elements in. Calling it with 0 gives you a pointer to the first element. So really, this get pointer call is the reverse of the 0 copy for getting data out. However, we did look at the 0 copy yesterday where we had the structure of arrays, where we have 3 component arrays individually. This call actually breaks that. So that's the disadvantage of doing something like this. This breaks the structure of arrays implementation. So that's something to think about. And with the 0 copy structure of array implementation that Kitware did as part of Sensei 1, they also analyzed the data array API, the API that VTK provides in data arrays for actually getting values out. They analyzed that for performance and made some optimizations to make it faster and more equivalent to processing a raw pointer, which processing a raw pointer is the fastest. The compiler can optimize that the best. But using the data array API these days is actually quite performant. If you wanted to do a 0 copy here from the SOA case, you would have to do a dynamic cast on, instead of a float array here, you'd do a dynamic cast to the VTK SOA data array template float, similar to what we did in the example yesterday for the 0 copy example. You do a dynamic cast to that type and see if you had one. If you had one, then you could get the individual component arrays out through its API. And if you didn't, then you could do this. So be aware that these get pointer calls are dangerous. And in fact, if you call this on a VTK SOA data array template instance, a deep copy of the data is made. That's how this API works in the new SOA array. Because if you didn't, then that thing would just crash because you have 3 arrays under the covers. Okay, so scrolling down, this is finally, actually, wait a sec. So we had just looked at this case where we had, up here, where we had a composite data set. Now when I scroll down, I'm going to look at the else case if we have a data set. So this is the legacy parallelization strategy where each rank has one and only one VTK data set. So it's basically the same thing, just written without the iterator, the composite data iterator. We're doing all the same things. We're getting the block ID. We're getting the autocorrelation implementation from DIY. We're downcasting to a float array, and we're getting a pointer to that data, and we're calling process on it. And finally, we're just returning true. So that's the autocorrelation analysis in its entirety. The thing that I kind of glossed over was actually the calculation itself. If you're interested, you can go in and delve into that in these classes here, this autocorrelation implementation, and you can see how that calculation is implemented. But this actually calls the computation, and this is all the mechanics. We've done a deep dive into all the mechanics of how the analysis adapter works. So in this section, what we've done is we've looked in depth at a data adapter and how you would write it. We've looked at specific code for this oscillators mini app. We've looked at the bridge code, the initialize, compute, and finalize that actually sets everything up, pushes data through Sensei at every time step. And we've looked at a specific example of an analysis adapter, the autocorrelation. Before I go on, are there any questions about that section?
About this initialize function, is it this initial that, where does it come from?
In the analysis adapter?
In the bridge.
Oh, in the bridge. That's completely up to you. It's completely arbitrary. The bridge code is all in your hands. So the bridge code is written to connect the simulation to the analysis backend. There's really no constraints we place on that. You need some code to do that connection. But it's up to you really how you do it. The mini app or the simulation, we'll call it. So let's say you have a CFD simulation computing airflow over a wing. When your CFD simulation starts up, you will call that initialize function before the simulation starts to execute. Once the simulation starts to execute, you will add a call in your simulation to call the bridge compute method. And then when the simulation ends, you'll call the bridge finalize method. Okay, so those 3 functions, they're used to set up the connections through Sensei, configure the analysis backend, push data through Sensei, and finalize everything, tear everything down, clean it up. But how you do that is up to you. These are just kind of examples, and we'll go through some more as well. There's actually, later in the talk, there'll be a full simulation instrumentation example too. Yep, good questions. So now we're going to do a deep dive looking at lamps with Sensei. So LAMPS, it's an acronym, Large Scale Atomic Molecular Massively Parallel Simulator. It's a pretty cool one. It's a molecular dynamics code. Can run in parallel with MPI, using a spatial domain decomposition of the molecule. It can be run on CPUs, GPUs, and Xeon Phis. And I guess it's written by Sandia National Lab. This actually shows this rhodopsin benchmark that comes with LAMP, and that's what we're going to use in our visualizations. It has 32,000 atoms in it, so it's a good benchmark. And the mini app that we've used here configures lamps to run this rhodopsin benchmark, and then we do some visualization with Osprey, which is a ray tracing library. Okay, so in situ for molecular dynamics. So LAMPS is a good mini app for Sensei, or a good example with Sensei. It's a very popular library. It scales up. It's can do a lot of different types of relevant computations for that domain. In our example, we're using it as a library. So LAMPS can be run as a standalone simulation. You compile it, you give it an initial condition file, and you set it off and run, and it computes stuff, and it dumps stuff out to disk. We're not going to use it that way. Instead, what we're going to do is we're going to use it as a library. We're going to have our driver application load up LAMPS, set it up, and then we're going to make calls into LAMPS to tell it to compute, to advance its solver, and then we're going to get the data out of it. So the advantage of this is that we don't need to touch LAMPS internals at all. It's not possible to do this with all simulations, but with LAMPS, it's possible to use it as a library. So this example, we've got LAMPS as a simulation. We're going to have a data adapter. We've got our driver code. The driver code is going to set LAMPS up, and our bridge will go in the driver code. In this example, we also have an analysis backend that was written just for this. This example, by the way, is by Silvio Rizzi. He's at Argonne, and the Osprey part was written from somebody at Ski in Utah. So the backend analysis does this rendering with Osprey. It's a software-defined visualization. It's a ray tracer. It's very fast. It does things in parallel using threading and vectorization. So it's a very optimized rendering library. And it will render much faster than something in VisIt or ParaView. Although I think in some of these backends you can actually use Osprey now. Okay, so here's our Sensei architecture. Of course, we've got our simulation, our data adapter, bridge, analysis adapter, and analysis. How does that change for this example? Well, it doesn't. But on the left, we've got our driver code. This is our main application using LAMPS as a library. We're configuring LAMPS, taking this input file that we read from disk. This will be the rhodopsin benchmark configuration file. We'll push that into the LAMPS library, and then we'll set LAMPS up to compute simulation. We're going to use callbacks that LAMPS provides. Our callbacks will trigger the updates of the Sensei analysis adapter. On the back ends, we've got a custom analysis adapter Osprey that was written just for this demo. So the data that's produced by LAMPS are particles basically saying the locations of the atoms. And there's some additional info, such as the atom type or radius. So this is the data that's going to be passed through Sensei, XYZ coordinates, and atom type. So LAMPS has these callback methods that get invoked. We're going to tell LAMPS to call these functions that invoke the Sensei execute on the analysis adapter for us. If you're interested in this topic, this coupling to LAMPS, using it as a library, basically, here's a link. So here's an example of the lamps callback for every time step. This is what we're going to tell lamps to call. And in our lamps callback, this is the data. This is the API from lamps itself. We give this to lamps. Lamps calls us. It gives us the data. So this will be a pointer to some set of arrays, probably the positions, I think. This is a pointer to the scalar fields arrays. Here we're going to just extract the bounds of the simulation. We're getting the atom types. And then we're going to pass all of this into through Sensei, set up the data adapter here, and we're going to execute. So lamps is calling that every time it updates the simulation. So there you have it. You know, at this point, I want to just delve into the VM for a sec and actually open up the Sensei code and just take a quick look at it, because I feel like this is a little too high level. So I'm going to go into the VM. I'm going to open up a terminal. Make the fonts a little bit bigger. In the SC17 directory, I'm going to go into the source code for this lamps work. It's in the software directory, and there's a lamps _ Osprey viewer directory. In that, we've got the driver, the libis. This is, I think, the rendering library, and the viewer. So inside the lamps driver folder in here, I'm going to go into the Sensei interface folder. So in here, I have all of the Sensei code from this example. So in this, let's see, maybe if I make the font just a little bigger. Yeah, so in here I've got our bridge code, I've got our data adapter code, and our analysis adapter code. So this is all the Sensei code right here for the lamps demo. Let's look at the bridge first. So the lamps bridge, here you have it. Initialize, set data, analyze, finalize. So set data in the bridge is going to be used to pass in data from lamps. Analyze is going to be used to push that data through Sensei into the back end. The initialize, finalize, set up, tear down. So let's look at the C++ side of this really quick. So here's our bridge, the actual code. We've got some global variables here. Data adapter, analysis adapter. Initialize is just going to create instances of these guys. They're smart pointers, by the way, so they'll get deleted. There won't be any memory leaks when things shut down. We're creating the data adapter. We're creating the analysis adapter. We're initializing both of these. So there's your initialize. Set data. This is going to be used to transfer data from lamps into the data adapter. We have to get that. Lamps is computing some updated values. We need to get those updated values and have them so that we can push them through the interface. You saw this call a second ago, how things are being called here, but basically we're setting the bounds, we're setting the pointers to the element positions. and the type of them, and basically the number. Analyze just executes the analysis adapter, giving it our data adapter. And we are releasing the data in the data adapter. So anything that's cached by this set data call, whatever's cached in there gets freed up. Finalize, again, these are smart pointers. Assigning a null causes them to actually be deleted. OK, so that's the bridge code. Let's take a look at the data adapter. Quick look at the header file. So this is what you'd expect. We're using polymorphism. We're deriving from the Sensei data adapter. We're going to have these pure virtuals that we have to override. Here they are, the get mesh, add array, get number of arrays. Very simple implementation, just returns one. Get array name, returns the name of our array, data we're calling it. So these two are super simple, done. And then we have these, which we'll have to go in the C++ code, the get mesh, add array, and release data. We'll take a look at those. Everything else above, up all of this stuff, is just custom stuff that you can add in. These are helper functions. The set bounds, we saw that being used in the bridge. Set data pointers, we saw that being used. So that's how the data is actually transferred from the simulation into the data adapter. Everything down here, again, this is the Sensei API. This is what's called from the analysis to actually access the data. OK, so this is our data adapter class, the actual implementation, constructor, initialize functions, set bounds. We saw this. This is how bounds are getting passed in. This libis stuff, this is all about the, the internal library that Sylvia is using. Get bounds, set data pointers. This is how the LAMP data is getting passed into the data adapter here. So as the data is passed in, if there isn't an instance of internals atoms, this is VTK smart pointer or float array. So if that guy isn't initialized, then he's going to create a new float array. And he's going to tell it that there are 4 components. He's going to set the number of tuples. So a tuple, in this case, we've just told it there are 4 components, so a tuple will be 4 values. And he's going to tell them there are n local of these 4 tuples. He's going to loop over the local values and basically assign them. So tuple is size 4 here. He's taking values out of the LAMP's data, this X array that gets passed in. He's casting it to a float star and then indexing into it, passing it into this 4 tuple, and then setting it inside the VTK data array. And this is using the VTK data array API. This is part of VTK, the set tuple call. So VTK data array documentation has that explained. You're just passing in a 4 tuple at index I, and the data array stores that. So this is how he's getting the LAMP's data, which is passed in this double star X. And so those are the positions, again, of the atoms and the type and the length of that. He's just taking that and converting it, stuffing it into a VTK float array. And he's caching that. Get mesh. This is interesting. He's not actually creating any VTK data object. Add array. He's not doing anything there. Release data. Okay, so let's look at this for a sec. Okay, so he's added this getArray function that returns a data object. And this returns the atoms array the float array that he constructed above. So what Silvio's doing here is he's doing something a little unconventional. I think what his Osprey backend is doing is it basically ignoring the Sensei API because he's returning null here. Actually, this is the first time I've actually looked in depth at this thing. So he's, in his analysis adapter, he's ignoring these, and he's probably going to downcast into a LAMPS data adapter, and he's using this getArray function just to return the array. So he's kind of cheating in a way. Let's take a look. So his analysis adapter, this is the Osprey renderer. He's deriving, again, from Sensei analysis adapter. And he's overriding the execute function, and he's added some initialize finalize. Let's just take a quick look at his execute function and see what he's doing. Oops. Okay, so execute. Here's his execute function. He's being passed in a data adapter. And yes, he's doing a downcast. So he's making an assumption that he has a Sensei LAMPS data adapter, this is his data adapter class. He's making the assumption that he has one of these instances. This is okay for him to do. This isn't going to work in general. So this is okay because he knows this application, it always has to have this type of data adapter. He's doing a downcast, which is the equivalent of a dynamic cast, and he's using this getArray function. So he's circumventing the Sensei API here, which is kind of a cheat, but it's okay. This just isn't going to work with anything else but his data adapter. He's getting bounds, and he's passing into this libis process. So the libis process call invokes the Osprey render. Okay, so yes.
Was the only way to do this that way, or?
No.
Or is this a best practice?
This is not a best practice. This is not a best practice. So what he's done here, let me see. This is where I would say Silvio has gone astray, is actually in his data adapter. So in his data adapter, he basically, these are pure virtuals in the Sensei data adapter base class, get mesh and get array and add array. These are where all of the action happens, where you're supposed to create a VTK object and add the array. He's ignoring these. He's just doing these default things where he's returning null, doing nothing, returning false. So he's basically circumventing. This is a bad idea. Don't do this unless you just want it to work with your backend. So his data adapter is only going to work with his Osprey backend. You can't take his data adapter and give it to Catalyst, which is a shame because Catalyst actually has an Osprey renderer. So it might be interesting to see how the difference is between pure Osprey and Catalyst. Oh, it might be interesting to see, how Libsim does with a molecule. So this is not a best practice, and I have to talk to Silvio, but this is a one-off. It's okay to do this if it gets your work done, but it's not gonna. So part of the advantage of Sensei is that you can mix and match these things, right? You could take this data adapter if it was implemented here with VTK data objects, and you could give it to Catalyst. You could give it to Libsim. he's basically taking that off the table. He has no flexibility. For his use case, I think he doesn't care about Catalyst or Libsim. He just wants it to work with his backend. So I think I don't think it's a best practice. I don't necessarily want to say anything bad about it either. Okay, so let's go back to our slide deck. Okay, so Osprey as an additional infrastructure. This is the analysis backend. So what his backend does, it uses the analysis adapter. It uses the data adapter we just saw in an unconventional way, gets the data and renders it using Osprey in the viewer window. So in this demo, we can run this thing. We can test it out. We can see it in action using the VM. So a couple things. When the thing first starts up, the window, we're going to have to zoom in and out to get it to see anything. The camera will be inside the rhodopsin. So we've got the steps of how to run this thing. Let's go back into the VM and give it a whirl. So let's get out of his code, go back into the home directory, go into the SC17 demos. And if you guys should also follow along on this and run it and play with it. So in the demos, we've got the lamps Osprey demo. So we'll CD into there. I think all of these demos actually have shell scripts to start them up that do all of the configuration of the environment. And that's the way that you can reproduce these and play with these after the fact if you want to run them and see how they are in action. So in this folder, we've got run-demo.sh, run-driver.sh, and run-viewer. So I think I've read these before. The run demo does this kind of tightly coupled thing. Run driver and run viewer run them separately, and that's the way I'm going to do it. Yeah, I had some problems with the run demo one. I think Jean did as well and contacted Silvio. So let's just take a quick look. He's going to load MPI. He's going to run MPI exec2 driver. And he's going to pass in this rhodopsin initial condition. So let's do that. Run driver.sh. And this starts up lamps. It's computing stuff. Let's go. Let's open a second terminal. We're going to CD again into the SC17 demos. Lamps, Osprey, LS. Now we're going to run the viewer. Let's just take a quick look at this run viewer. Shell, he's setting up the environment. He's telling Osprey to use gallium, tell mpitch that he's going to be multi-threaded, and he's setting the parameters on the viewer. So let's run this. Run viewer. And it started something up. I see a window popping up. And we're connected now. So let's see if I can get this to work.
On both of the terminals, do a module purge so that you get a clean environment before starting the animation.
So Jean is going to show a movie. This thing's obviously rendering stuff. The user interaction, I don't know, it might need some work, I don't know. You guys get the point. It's sending data, it's rendering it. Jean has a movie from the author. When Silvio runs the demo, it works fine. It's just pilot error on my part that I don't know how to use his interactive, system. So Jean is actually going to jump in here and show a movie from Silvio.
Okay, so this movie I'm showing here was sent to me by Silvio, the author of this coupling of lamps and osprey. This is actually a new method he's using at this point, in that he runs three different processes. The first one is the lamps solver itself. The second one is a back-end renderer, and then he streams the pixels from that renderer to his local desktop. And this is what we see here on the interactive window that is running. This is really just a pixel buffer copy from the remote rendering engine to his local desktop. Okay, so this is a new iteration of this coupling, if you want, and it's work that has been submitted to a visualization workshop, so not yet published, but I'm hoping we are now in close chatting with Silvio, because one person here in my group, Victor, if you know him, his intention is also to do the same thing for Pitts Daint with the GROMACS application. So if some of you here are using GROMACS, I'm hoping to have this type of functionality available, let's say, within a few months. Okay, it's going to take a little bit of architecture and debugging to get that going. But this would be really the idea, running both solvers and renderer locally on Pitts Daint, and then streaming the pixels back to your desktop at the university or wherever you are. Okay, so stay tuned, as we say. This is a work really hot off the press and still under development. Good.
Yeah, I'm so glad you have that movie. It does it more justice than me.
Yeah, I think it does. I think it does. And I myself am having trouble running the original demo of Silvio on the VirtualBox. So.
I don't know what I did, but I got it to work, and when I tried it the other day, it worked, and now today it's not working. So
all right.
It's just pilot error.
Yeah. Oh, okay.
Oh, beautiful.
Okay.
You got it to work. Sweet.
Oh, wonderful.
So can you share the magic that you did with the mouse to get it to zoom out?
Just right-click and up.
Right-click and up, okay. So I wasn't sure if it was up or down, so I may have been going the wrong direction.
Beautiful. What do you want to do? Are you at a good point?
This is a good point to
Okay,
take a break,
cool.
because this is the end of the Osprey
Yeah,
section.
okay, perfect. Okay, then on this interactive molecular stuff, we're going to take a break. Okay, keep your window open here so that we can all stop by your laptop to watch the window. Let's take a coffee break. Okay.